Okay, so this is the expression in the book. And this, in the book, what the book calls gamma is what I call alpha bar or beta. It's the power of the first term. To be honest, I don't really see how the book obtained this relation. So let me first look at my relation. These are the two equations I obtained. I should probably look a bit more in more detail, but let's see let's assume that what happens when n is very, very large, larger than any other number over there. That was our first task, to show that if n is very large, the wave function we obtain is not normalizable. If n is very large, that equation tells me that you see, this term, this one, becomes very large, the n plus first term. Among the n plus first terms, that is the dominant one. So the first equation basically simplifies to a n epsilon minus 1 minus n bn plus 1. This is equal to 0. That's the first equation. N.
PPN'in başındaki n hangi n?
This n.
Tamam.
The second equation reduces to bn epsilon plus 1 plus n times an plus 1. This is equal to 0. So let's see, the first equation tells me that bn plus 1 is epsilon minus 1 over n an, and now if I use the second equation, it tells me that this is equal to epsilon minus 1 minus epsilon plus 1 over n minus 1 bn minus 1. No. You see, this equation tells me that an plus 1 is equal to minus bn over n epsilon plus 1. But here I have an, so I have to replace n with n minus 1 everywhere. So bn plus 1 is actually 1 minus epsilon squared divided by n minus 1 bn minus 1. Or square root of 1 minus epsilon squared over n, square root of 1 minus epsilon squared over n minus 1, bn minus 1. So if I change n by 2, I get two such factors. So?
Hayır, kök içinde 1 eksi epsilon kare, 1 artı epsilon kare olmuyor mu? Ben yanlış dedim.
Why should it be? Both are 1 minus epsilon squared. But that tells me that bn plus 1 is actually proportional to 1 minus epsilon squared under the square root divided by n factorial. For very large values of n, it will behave like this. So, okay, if I go back to my earlier argument, well, there's no factor, such factor 2. This is what a and b n will behave like. Now, if I move over here, there's no such, this 2 to the n is not over there. There's no such factor 2. There's no such factor 2. But still, my argument doesn't change. You see, my wave function, u and v, they were written as x to the power beta sum over n a n or bn x to the n e to the power minus square root of 1 minus epsilon squared x. But now, this series for large values of x behaves like e to power square root of 1 minus epsilon squared x. It doesn't go to 0. That's the crucial thing. For very large values of x, that doesn't go to 0. Well, this diverges. So my wave function is not normalizable. But this is assuming that my series does not, this sum contains infinitely many terms. If n becomes very large and non-zero, this is how it will behave, and I obtain a non-normalizable wave function. So it only tells me that this series, this recursion relation, should end. I should have a finite number of terms in my summation. Now, how do I get that? Well, I will switch now to the expression in the book. I'm sorry that I have to just go back and forth. So this is the expression that the book gives me from the same equations. So I should have missed something in my computation somewhere. So what does it mean? It just means that let's say a n prime plus 1 should be equal to b n prime plus 1 should be equal to 0. This is what I want in my expansion. So choose I is equal to n prime plus 1 in my recursion relation. So that relation tells me that 1 minus epsilon a n prime minus z alpha, well, that is already 0, minus 1 minus epsilon squared, or 1 over 2 b n prime. This should be 0. And furthermore, 1 plus epsilon b n prime minus 1 minus epsilon squared 1 half a n prime. This should be equal to 0. What does this tell me? 1 minus epsilon minus 1 minus epsilon squared and 1 minus epsilon squared 1 half 1 plus epsilon a n prime b n prime. This should be equal to 0. I don't want my a n prime and b n prime to be both 0. The first time where both of them are 0 is at n prime plus 1. So this tells me that the determinant of this expression, did I write it right? Yes. The determinant of that expression, oh, sorry.
Bir yerde 1 bölü 2 var şimdi.
Hı?
3 term. Bunun üstünde bir şey yokmuş. Bir tanesinde 1 bölü 2 var. Bir yerde de olması gerekmiyor.
No. Okay. So determinant of this thing is equal to 1 minus epsilon squared. So there's a minus sign somewhere else. This is minus. Minus 1 minus epsilon squared. It is 0. That's fine. So we have, yes.
Bunun olması için sağ üstteki termin de kök içinde olması gerekiyor.
No.
Ama 3 bölü 2 geliyor çarpınca da.
No.
Sekini diyor birinci.
Yes, this one is squared, sorry. So determinant is 0. Fine. So I have, but determinant equal to 0 basically tells me that both equations are the same equation, which tells me that 1 minus epsilon a n prime is equal to 1 minus epsilon squared b n prime, or square root of 1 minus epsilon over 1 plus epsilon is b n prime over a n prime. Okay, this is one relation I have. This is the last terms. And let's see. Now let me look at these equations. that equation already tells me. Let's see what I can tell about this. Let me multiply the second equation by 1 minus epsilon under the square root, the first equation by 1 plus epsilon under the square. Why do I do that? If I do that, I get, in the above expression, I have square root of 1 plus epsilon, 1 minus epsilon ai minus 1, blah, blah, and square root of 1 plus epsilon, or 1 plus epsilon square root of 1 minus epsilon bi minus 1 equals 0. That's the first equation. I'm just tired of writing all the terms. And the second equation will give me 1 plus epsilon square root of 1 minus epsilon bi minus 1. It is this term. And the first line will be minus 1 plus epsilon square root of 1 plus epsilon ai minus 1. It is this term. So basically they are the same. I get rid of them. So this equation also tells me what remains is I have the ai and bi terms remaining. So I minus 1 terms will be eliminated. I end up having bi over ai is equal to some ratio. This is for arbitrary I.
So should be like I dependent?
It depends on I, but you see, but you are right. We also have this relationship. When I set I is equal to n prime here, this should be equal to this expression.
So n prime is a specific value, or is it?
Hold on. For the time being, n prime is arbitrary. It can be 0, 1, 2, up to infinity, any number. But for a given n prime, this is an equation for epsilon. Hold on. So, I repeat, n prime can be 0, 1, 2, up to infinity, any number. I'm just saying that the next term in the summation is 0. So my sums is a n x to the n contains n prime terms. That's what I'm saying. N prime can be at least 1. I have n prime terms. For each n prime value, I have such an equation which gives me an energy value. Now I have all infinitely many energy eigenvalues. Each energy corresponding to a different n prime value. Okay, so the result is this expression over here. So what did we do? We identified the differential equations. Then we identified how it behaves at large distances. So that, and for it to be normalizable, we said that, okay, it has to behave like this for large distances. Then we factored out that large distance dependence and assumed a wave function that is equal to the large distance dependence multiplied by some series expansion, which is not a Taylor expansion because of this x to the beta term. They are not analytic, and in fact, for the lowest value, beta can be even negative, so it diverges at infinity, at 0. But still, no problem. because even that divergence is integrable, so all the probability interpretation is still valid. Then what did we do? We found, using our differential equation, we obtained recursion relations for these coefficients a_n's and b_n's. And the recursion relation, well, I obtained the wrong one for some reason. This is the recursion relation we have, which relates a given a and b_n value to the previous a and b_n values in that sum. Then we said that, okay, unless this sum contains finite number of terms, you see here, this equation tells me AI and BI in terms of AI minus 1 and BI minus 1. So if you know AI minus 1, BI minus 1, you know what AI, BI is. I mean, if you like, you can just write this as a matrix equation. So this is actually AI, BI is equal to some matrix times AI minus 1, BI minus 1. So if AI minus 1, BI minus 1 is 0 at some order, all the remaining ones will be 0. So unless that summations multiplying my asymptotic wave functions, these ones, unless these terms contain a finite number of terms, those summations change the asymptotic behavior and my function no longer goes to 0 at infinity. So those sums have to end at some value. At which value? Well, it can be any value. And depending on how many terms I have in that sum, I have different eigenstates, I have different eigenvalues. And then how did I determine them? Well, I have these two equations, which also allows me to calculate the ratio of any two terms. This is valid for any I, and in fact, this expression over here depends on I, but that doesn't depend on A's or B's, so I can calculate that ratio. And then I said that if the expansion ends at some point, well, just instead of I, put that point. That already gives me a ratio between these A's and B's of the last non-zero value term. They should be same. This general expression of the ratio and the ratio of the last term, they should be the same, which gives me the energy.
So previous terms are not related to energy. Only the last the value gives the.
Well, how many terms are there in my expansion is what determines the energy. My energy depends on that number of terms.
But whatever the number of the terms.
You see, all the terms are related to each other.
Last term is this ratio?
No, all the terms are related to each other because of this recursion relations. I cannot say that the only last term determines it. All the terms depend on each other. But saying that, okay, in that sum I have 5 terms, then the energy should be this. If there are 6 terms, then the energy should have some other value. And this is the general expression of the energy. Oh, where did I have it? Let's make a Taylor expansion.
Yapış hareket ederken ne güzel bir torunumuz var. Biraz hızlanınca ne oluyor fark et.
C'yi bir alırız.
I'm gonna ask a really dumb question. What was you and what was me?
Hold on. This is the first term. But this is nothing but the solution of the hydrogen atom in the non-relativistic limit. Whereas this is the principal quantum number. It starts from, well, okay, that's the principal quantum number. Some constant over n squared is this is the rest mass energy. So if you just subtract the rest mass energy, you get the energy eigenvalues of the hydrogen atom. Plus higher orders in Z alpha squared gives you higher order corrections, the relativistic kinetic energy correction and all the other corrections you have.
So if we use the higher order terms, we getting close to the exact solution of the
Sure.
relativistic one?
Well, you're approaching the relativistic solution. There is one issue though. You see, energy depends on J. In principle, depends on J, let's say. So, if two states, let's say the S states and P states, you can have the same J value.
Or like S,
You see,
S and 2P?
S and P, this is you have the L is equal to 0, S is equal to 1/2, J is equal to 1/2 state, but you also have L is equal to 1, S is equal to 1/2, J is equal to 1/2 state. Let's say that both of these corresponds to n prime is equal to 0. Let's see. Then n, the corresponding n will be n prime is 0, J is 1/2. Yeah, 1/2, 1/2, n is 1. No, yeah, no. Yeah, n is 1. What did I do wrong? N is equal to 1, cannot be L is equal to 1, so this is probably n plus 1.
Son anda şeyi tutturamıyoruz.
Ne?
Hidrojen atomının enerjisi.
N starts from 0, n starts from
N ve L arasında böyle ilişkilerine çalışıyoruz. Niye?
Hı?
Are you looking for a relation between L and N?
O içerideki ifadeyle en arasında bağıntı kurmaya
Okay,
çalışıyoruz.
but-
Degeneracy'yi göstermeye çalışıyoruz. Degeneracy'yi gösteremedik. Bence
No, I have the degeneracy. Oh, n prime cannot be 0, n prime is 1, sorry. That's the minimum value of n prime. I cannot have 0 terms in my sum. I should have at least 1 term in my sum.
N prime and J are independent of each other, right?
Yes.
There is
No relation between them. So and the orbital quantum number in both cases is 2. So I have these n is equal to 2 states. And n is equal to 2, L is equal to 0. L is equal to, so these two states, N, L, M, NL is equal to 2, 1, and NL is equal to 2, 0 states should be degenerate even in the relativistic treatment. Experimentally, they turn out to be non-degenerate.
Niye tutuluyor?
We have the L and J quantum numbers in your book. This is page in your book, figure 8.2. There's a slight shift. You see, this is the full relativistic treatment. This is true for this expression also in the full relativistic treatment with a 1 over r potentials. We have all the spin orbit couplings, spins interact, spin effects, etc. All of them are already included.
Does higher order term shift the degeneracy?
Which higher order terms?
Oh, that
You see that degeneracy that should be there is also already here. It depends only on J and N prime. That's the difficult. That's the issue. So this treatment, although we calculate all the relativistic corrections, doesn't lift that degeneracy, but still the states are degenerate. So that this is what's called the Lamb shift. It turns out that, okay, here we are just using the 1 over r correction. You can calculate 1 over r potential. Well, the potential have other corrections to 1 over r. Okay, in field theory, you can just calculate higher order corrections to this potential energy that comes with Z alpha. Now, this is Z alpha. There's an alpha squared correction. Which is proportional to Dirac delta R. So this is the cause of the Lamb shift. Now that is the shift between the state energy levels that should be degenerate in the relativistic treatment. In the full relativistic treatment, they have to be degenerate, but they turn out to be non-degenerate. So which basically told us that the potential between the electron and the proton is not just the 1 over r, there is also this Dirac delta correction to that.
Why doesn't the non-relativistic version have that correction?
No, the potential has that correction.
So
The Coulomb, the correct potential between an electron and the proton or two electrons is not just 1 over r, there's 1 over r plus that Dirac delta term.
So why doesn't it lift the degeneracy in the hydrogen atom for the non-relativistic case?
It does.
So
If you add this term, it does change the degeneracy.
So hydrogen atom isn't degenerate after.
I see. Here is the hydrogen atom. What you calculate is not the hydrogen atom. This is the hydrogen atom. This is the experimental value.
Yeah, is this the reason that if we not adding that part to the potential, but using the relativistic energy formula, then we get the classical limit, right?
Let me just...
This is why it's working.
Hold on. Let me just make some clarification. This is the hydrogen atom. Those are the shifts of the hydrogen atom, okay? Not the computations that we do. We are basically making a model in order to reproduce what we measure in the experiment. Okay. So, what is the hydrogen atom? We have the electron, proton. You start by saying, okay, the electron and the proton, they have this 1 over r potential between them. Okay, great. You can try to solve this problem using non-relativistic quantum mechanics, but we know that non-relativistic quantum mechanics is just an approximation to the relativistic case. You can solve it in the non-relativistic case. You can solve it in the relativistic case. Just know your limitations. But if you solve with 1 over r potential, these two states, whether you use the relativistic case or the non-relativistic case, these two states should be degenerate. Now, in the non-relativistic case, you can just guess that, okay, it's non-relativistic, you calculate relativistic corrections, maybe relativistic corrections will lift that degeneracy. You might hope that it will happen. But what we have shown over here is that even the full relativistic treatment does not lift that predicted degeneracy. Because that prediction should not be there, because experiment tells us that there's no degeneracy there. The energy levels are slightly shifted. That shift is given a name, which is the Lamb shift. And of course, now there is a question. We have the full relativistic treatment, which doesn't agree with the experiment. What is the answer to this discrepancy? And the answer turns out to be what is called the Lamb, comes from the correction to the potential. The potential between 2-point particles in the full field theoretical framework is not just Z alpha over R, there are corrections to that, which are proportional to the Dirac delta function at r is equal to 0. If you calculate those terms, you can add that term in the non-relativistic treatment, in the relativistic treatment, whichever one you want. That term will contribute to the S wave, but it will not contribute to PD or higher angular momentum cases. So that term changes the energy of the S states, hence lifting the degeneracy between the S and P states.
But MPPs are still degenerate, right?
Now, if you want to do more and more, you can add more and more terms, because the proton is not a point source. That's another problem. So the proton is not a point. You can take into account the size of the proton, add even more corrections. Even the weak interactions contribute to the interaction between an electron and the nucleus. No. It is done by experimentalists. It's measured, and in fact, that is one line of research for CP violation. So we are just building models here that are trying to reproduce what we measure experimentally. Yes?
Yani relativistik yaklaşım değil, potansiyelin correction'ları sağlıyor. Deney yaklaşımımız.
Yes.
Tamam.
Well, relativistic corrections also make us approach to the observed values.
Ama lamp shift'i katmadan koyunca relativistiğe bunu classical çıkıyor.
Let's say that non-relativistic experimental result, let's say that it is 5.12, I'm just making up numbers. Non-relativistic result gives me 5.02. First relativistic correction.
Potansiyel için mi correction bu şey?
Computation makes my answer 5.05. I'm approaching full relativistic treatment. .11. Correction to the potential. Again, I emphasize I'm just making up numbers. Non-relativistic treatment, 5.06. It also modified that one. First relativistic correction, 5.10. Full relativistic treatment, 5.123. At least this is the hope. The more corrections you calculate, the closer you get to the experimental value. There are corrections due to the form of the potential, there are corrections to the relativistic effects, there will be corrections from weak interactions, strong interactions, etc. But let's say that if your experimental setup can only measure one digit after the decimal point, so I mean, you are happy with this, you will be happy with this, you should be happy with this one, they all are the same. Once your experimental setup makes measurements up to 3 digits after the decimal point, then you can distinguish between this one and this one, and this one. Okay, any last questions?
What was you and what was you?